Okay, thank you. I'm Juma Bukomba. I'm from the University of Wisconsin-Madison, and I recently just became a PhD candidate. And my quality of life, I feel like has become much better. And I know if you've been in this kind of experience, you know what I'm talking about. So today I'm going to talk about one of my dissertation chapters. This focuses on the study of ammonia reduction management practices in applied, impact of ammonia reduction management practices in land applied manure on nitrogen losses and nitrogen use efficiency. So to begin with, Wisconsin still has the throne being considered as the dairy land of America. And this is because the state has over 6,000 dairy farms. This industry does contribute about 45 billion US dollars to the economy of Wisconsin. And this large industry does lead to tremendous production of manure as a byproduct. And this is actually utilized by farmers in different ways. One of the ways is biogas production, whereby energy is produced, and this can actually be utilized on agricultural farm. And then a big number of these farmers use this manure as an organic source of nutrients, whereby they apply it and then it can be able to supply certain nutrients that can boost agricultural productivity. We also see that there are some farmers who apply the manure with the intention of it acting as an organic amendment to improve certain soil characteristics, for example, improving water moisture, improving soil organic matter, and measure them. So within manure, it does contain a lot of nutrients, but one of the key nutrients is nitrogen. And we see that through the chain of manure management and handling, we see these nitrogen losses, especially as emissions through ammonia volatilization and nitrous oxide emissions. For example, right from the point when we see this animal excreting this manure, we see that we have about 6% of this nitrogen being lost to the atmosphere as emissions. This number does increase to almost 30% during storage. And research actually shows that there is a tremendous amount of nitrogen that is actually lost when we get this manure and apply it to agriculture soils. It comes to almost 0.5% of that nitrogen just being lost to the atmosphere as emissions. On top of that, we see that about almost 25% of this nitrogen is actually lost out of the soil system. And this is a significant number, like if you take the cumulative amount of the nitrogen being lost out of the system. So my research does concentrate on this component, whereby we apply manure onto the agriculture soils, and then we see these nitrogen losses across the system. So I know most of this data you already know about it because I've attended some sessions whereby they already mentioned about some of these. But I want to mention that most of the emissions actually is actually ammonia, and the livestock does contribute about 60% of these ammonia emissions on the US scale. The loss of this ammonia does lead to loss of the nitrogen value in this manure, meaning the crops are losing that nitrogen that would actually support them to build that physiological development. Like Rhoda mentioned, we also see that ammonia can lead to formation of fine particulate matter as it reacts with sulfur and the oxides of nitrogen, and this can cause respiratory issues. We also see it leads to atmospheric deposition, whereby this can actually be a serious concern, especially in ecological systems whereby nitrogen can be a limiting factor and can also be an indirect contributor of greenhouse gas emissions. So how does my project come in? So I'm just going to refer you to this figure. So what we do is we do have what we call ammonia reduction practices. We focus on these practices and then compare the emissions across these different manure ammonia reduction practices, and then compare the trade-offs across these different practices with nitrogen leaching, and also looking at corn silage and nitrogen use efficiency. So this is how the whole scope for this particular project is. So in terms of the experimental treatments, we have those three main typical manure application practices. That is surface manure application, manure injection, manure incorporation, and then we kind of spice it up by adding some two different treatments, that is using urease inhibitor. And this is mostly because we have seen that urease inhibitor has actually been well studied when it comes to chemical fertilizer applications to reduce ammonia volatilization. But when we come to manure, we actually don't see a lot of data like showing how this urease inhibitor could actually have a potential effect in reducing these ammonia emissions, especially understanding that the biggest component of nitrogen, about 60%, is actually urea, which could actually be converted into ammonia. So we have urease inhibitor and then injected into the soil, and then urease inhibitor that is surface applied. And of course, we have our plots where we don't have the manure as a control. This is a randomized complete block design with these 6 treatments. These are replicated 4 times. This is a 2-year project. Today I'll be presenting the preliminary data from our first year project, and this is conducted at one of our research stations that is called Arlington Research Station in Madison. So how are we measuring these gas emissions? We are using the USDA GraceNet protocol, which does employ a chamber-based methodology to quantify these gas fluxes. We use an FTR, which we use to measure these gas concentrations across these experimental plots. So what we do is we do apply the manure into these experimental plots, come with the chamber, which is left permanently in the field, only removed during certain farm operations, for example, planting and other activities. But during a particular gas sampling event, we come with a lead. And then this is Becky holding the lead. This lead has 3 vents. One is the air vent. We have the sample out vent, which connects to the FTR, taking the sample for quantification. And then there is a sample in vent that brings the sample from the FTR back into the closed chamber. That way it establishes a closed loop system, and this enables us to take the cumulative concentrations of these gas emissions within a period of 8 minutes. We also take some auxiliary data measurements, for example, take soil samples that we can be able to quantify for inorganic nitrogen concentrations, look at soil temperature and moisture to see how these different variables could be influencing these emissions that we are taking. So for the nitrogen leaching methodology, we are employing a self-integrating accumulator. This particular method is developed by a German company called TerraQuart, and has been used by several scientists to estimate nitrogen leaching. So basically it has a PVC that is about 10 centimeters in diameter and then 10 centimeters in height. At the bottom of this PVC, we put a fine mesh, and then inside, we fill it with a mixture of mixed bed resins and silica sand in a proportion of 1:2 by volume ratio. So during the deployment of this resin cartridge, we do dig a pit of about 100 centimeters, and then at a depth of 90 centimeters, we dig these horizontal pockets whereby we insert these resin cartridges vertically beneath this undisturbed soil. And this is particularly important because it helps us to maintain that natural, that soil structure, which is essential for the natural flow of water during these nitrogen leaching measurements. So in each experimental plot, we deploy 3 cartridges, and these are left in the field for about 6 months, after which we retrieve them and then take them to lab for quantifications of nitrogen leached in those experimental plots. We planted corn silage, and this is my beautiful corn growing. We had it, the growth cycle is about 90 days, and harvested it like about 65% moisture content. This is us harvesting, and then we do take yield data, send some samples to the lab for quality metrics and other parameters that we evaluate on the corn. So these are the preliminary results, and I'm going to present the cumulative ammonia emissions within 96 hours, and this is because ammonia is kind of interesting in that we usually see, when we apply manure, we usually see like high emissions within the first 3 to 4 days, after which it kind of just flattens out down the growing season, so you don't actually see a lot of emissions. So these are my hours after manure application, and then this is my cumulative ammonia emissions measured in grams per acre. So looking at this graph, we do see some very typical trends. Let's just focus on those treatments where we don't apply the urease inhibitor. So we have the surface manure application. We see this is having really way high emissions. So when you compare it with the injection, which is this light blue line, it is the injection actually has very low emissions compared to the surface application, and the incorporation is just somewhere in between there. But incorporating the urease inhibitor and comparing it with these parallel treatments, we observe that when you come to the surface manure application, there is actually a reduction when you apply your manure on the by surface, but incorporating the urease inhibitor, and this is about a 30% reduction. So there is kind of a benefit when you apply with urease inhibitor, but that trend is actually not kind of visible when we inject the manure and apply the urease inhibitor. So it may not provide that agronomic benefit when it comes to manure injection using the urease inhibitor. So for the potential nitrogen leaching, we also see some interesting trend here in that for the treatments where we do see like those high emissions, we actually see, okay, time is coming up. So we actually see for the treatments where we see those high emissions, we actually see lower potential nitrogen leaching compared to these treatments where we had very lower emissions. And this could be because in such treatments, we are having a lot of ammonia that is being converted into nitrates, and this could be susceptible to nitrogen leaching, especially given that we have that anionic nature of nitrates that makes it very mobile into the cell system. For the corn silage, we also see some significant differences comparing what I would call the surface manure applications with the surface manure applications. But we do see that generally we are still seeing high corn silage yield compared to the surface and the no manure applications. For the indices of nitrogen use efficiency, looking at corn nitrogen uptake, we really didn't see a lot of differences across these treatments. And that could also be associated with the fact that I forgot to mention that in one of my previous slides. We really did see a lot of nitrogen concentration in our plots that did not have manure, and this means that this could actually have kind of reduced the treatment effect that we might have seen, especially when we applied manure across these different manure application systems. But like I say, this is a preliminary result, so we are repeating this project to see how this dynamic kind of plays out, and we're going to do this on a different plot to see maybe if we could get that more of a treatment effect across these treatments. So as the key take-home messages, we do see that subsurface manure applications like incorporation injections are effective in reducing ammonia emissions. However, these practices tend to increase nitrogen leaching, and this does mean that much as we are looking at reducing ammonia emissions, it is important for us to actually still consider like other mechanisms of reducing this nitrogen leaching across the soil. We see that if you use manure injection with urease inhibitor and just manure injection, there are environmental outcomes of reducing ammonia emissions, but we really don't see that agronomic benefit in terms of using the urease inhibitor across these experimental plots that we have. There's a potential benefit of using a urease inhibitor to reduce ammonia volatilizations, especially if you're applying manure by surface applications. And I would say these are my faculty members I work with. For my committee members, Dr. Becky Larson is my co-advisor, and these are my other professors on my committee. I want to recognize the students and staff. Brian is here, Tyler is here, that work with me to execute these projects in the field. And I want to mention that this project is funded by the National Science Foundation. Thank you so much. I'll take any questions.